All right. Today we are going to talk about large language models for macroeconomics. Large language models are rooted in computer science, but they are penetrating our daily lives. Understanding their evolution and capabilities provide the basis for understanding their potential impacts on every aspect of the economy, from labor markets to productivity and innovation. What are large language models? A large language model is a sophisticated, pre-trained statistical language model based on neural networks. What are neural networks? A neural network is a computer model inspired by the brain that learns patterns by passing inputs through layers of neurons. In a neural network, each layer transforms the, for example, input numbers, and after enough training through a number of layers, the network can recognize things such as images or sounds or text. Now let me give an example, actually two examples. One is one layer neural network and the other is two-layer neural network. Let's start with one layer neural network. Suppose there is a vector of two numbers, say x equals 2 and 3. It's a vector. And one layer network consists of one hidden neuron layer and its activation function, and output neuron layer, and it provides the final value as an output after this process. The hidden neuron works as follows. It consists of weights and bias. Since we have two numbers, we need two weights. And these weights works like coefficient of a function, and bias works like an intercept of a function. So given the input number 2 and 3, we apply the weights of 0.5 and 1.0, and then we add the intercept 1 at the end. Then this first hidden neuron will give us number or the value of 5. And then at the end of this neuron, we decide whether we want to activate this neuron or not. The activate function can be anything, but usually we use this ReLU function, which is just a maximum function. The maximum function decides the value of function by comparing two numbers between, especially 0 in this case, and the given value. Since the given value is 5, if we compare the number as with 0, then 5 is greater. So we take 5 at the end. So it's activated. Now we go to the next neuron, the final neuron, output neuron layer. And this output neuron layer also has weight and bias. we need only one weight because we have only one value, 5. So weight is 2 and bias is suppose -3. Then we apply the weight like a coefficient and we apply the bias like the intercept. Then we get number 7 or the value 7 out of this simple layer of neural network. So that's simple. That's one layer neural network. And let's take an example of two-layer neural network. It's exactly same, but we have two values from these hidden neurons. We have two different hidden neurons, and we will get two different values from these two different hidden neurons. And then using these two different values from hidden neurons, we will get one number out of this output neuron at the end. The output neuron now has two weights and one bias so that we can apply this bias like an intercept. And we get 6.5 out of this two-layer simple neural network. Since this is not the point, this is not computer science course, so we are going to just have a broad understanding about how neural network works. But anyway, if we have two input numbers and two hidden layer of H1 and H2, then we will get two numbers and two values or two values, two outputs from the hidden layers, and then using these values from hidden layers, we get the final output, which is 6.5. All right. So that was neural networks, and based on this neural network, large language model is generated. All right. These large language models, LLMs, are massive neural networks that have been trained on an immense amount of text data. We only took two numerical values in the example, but large language models take immense amount of text data, and the training is to understand or generate or process human language. Okay. Up to the development of large language models, the computer scientists went through three previous steps. So success of today's large language models is the result of decades of research evolving through four distinct stages, including the large language models, the current stage. So the previous three stages include statistical language models and neural language models, and then pre-trained language models, and then now we have large language models. All right, statistical language models are developed especially during 1990s and 2000s. The representative model is an n-gram model. These early models saw language as a simple sequence of words, meaning a vector of words, and they were called as n-gram. These models predicted the next word based on statistical counts of preceding words using maximum likelihood estimation. If you took econometrics already, you know what maximum likelihood estimation is. So this is a way to calculate the probability given some parameters, right? So that's how the statistical language models are. So they produce a probability distribution for the possible next words of at the end of some sequence of words. These models actually struggled with words or phrases they had never seen before, often assigning them a zero probability. It's called data sparsity problem. So let's take an example to understand what data sparsity problem is. Let's think about an example of classifying a product review as positive or negative by the statistical language models. All right. Let's take a 2-gram model and let's classify a review like the phone is great. And let's think about the other example. The phone is excellent. The model would look for word pairs like is great because it's 2-gram model. So it's 2 words model. And if we just give an example to the model that the phone is great is a positive review, then this model will look for the reviews that contain is great, the sequence of these 2 words. If we saw a high frequency of these grade appearing in reviews, then it will classify the review as positive review. So the phone is great. Then it contains is great. So the model classifies this review as positive. Now, let's think about the phone is excellent. A review contains these words. We know that this is positive review right away, but the model has never seen this word before. And the model designer did not give that is excellent is similar to is great. The model designer did not give any hint about that. Then, since the model has no idea what excellent means, so the model might not classify the review correctly. It just provides an error. Okay, so this is called data sparsity problem. Since the model has never seen the other word excellent before, so it just gave an error instead of positive determination or classification. So afterwards, in order to overcome this kind of shortcoming, the model developed 2 neural language models. So this model was kind of prevalent between 2003 to 2017. It's not long ago. I vividly remember that I struggled with learning this model. So it includes a feed-forward model, recursive neural networks, and long short-term memories. To solve the data sparsity problem, researchers created this model. These models began to map words to multi-dimensional continuous vectors. This means numerical coordinates like a vector in a xy plane, like a vector like this. This allowed them to measure the semantic similarity between words regardless of whether they had appeared together before or not. However, these models were task-specific, meaning they were trained for one job at a time, separately for each application. So the model is trained for machine translation, and then from scratch, the model should be trained for speech recognition. And then again, it cannot be recycled to other purpose, but it should be again trained from scratch for web search. So this is an example of, again, classifying a product review as positive or negative, but by the neural language models. So it goes beyond the simple word count, but it represents words as vectors like this. So it shows now excellent is similar or close to great. So we have solved the problem of statistical language models or data sparsity problem. The vector for great would be very close in this vector space to the vector for excellent. And the model analyzed the review, the phone is excellent, and yes, determine that the review or classify the review as positive. Now, again, the limitation is that it cannot be recycled to other purpose or other text. So you'd need to train a brand new model from scratch just to do product review classification and translating the review into Spanish. So this is one thing. You need like 5 days training for these models. And then in order to translation of the reviews, you need another 5 days training from the scratch. That's the limitation. And then in order to overcome this shortcoming of neural language models, pre-trained language model became the dominant language model. All right. So it has been since 2018. The famous examples would be Elmo, BERT, and GPT-1. This marked a major shift. Unlike neural language models, pre-trained language models were task agnostic. So the pre-trained model can be transferred to other tasks. So you don't have to train the model from the scratch for machine translation and then again train this model from scratch for speech recognition, etc. You don't have to do that. But the models were first pre-trained on a huge general text corpus, for example, Wikipedia, to learn broad language patterns. Then the machine now was able to talk like a person. Then it can be fine-tuned with small amount of specific data for a new downstream task. Now, you want this machine to translate Spanish to English, then you need to fine-tune this model with a small amount of specific data, like 10,000 examples of translation from Spanish sentence to English sentence. This pre-training and fine-tuning paradigm made the models much more versatile. Okay? So let's take an example of product review. So a large language model would first be pre-trained on a massive general corpus of text. Just think about Wikipedia. To learn the general relationship between words and sentences, it wouldn't know anything about product reviews yet. Then you would fine-tune this pre-trained model on a smaller specific data set of product reviews. We say smaller, but it is like 10,000 or 20,000 sentences. The model already has a broad understanding of language, so it can learn, it learns the new tasks much more efficiently. All right. The advantage is that after pre-training, the knowledge gained by the machine is transferable, so you don't have to train this machine or fine-tune this machine over and over time. All right. Now, from the pre-trained language model, large language models are kind of distilled. That is, since 2020, typical example would be ChatGPT. Large language model can be seen as a subset of pre-trained language models distinguished by their massive scale and additional capabilities. They are far bigger than their predecessor with billions of parameters. So it is like a regression equation, a set of regression equation, but the parameters are like billions, tens of thousands of billions. They are not only have better language understanding and generation abilities, but also they possess unique abilities such as few-shot learning and in-context reasoning that became practical only at their massive scale with tens of thousands of billions of parameters. All right. Now let's take an example of product review. So given a review like the product is amazing, I've never been happier, you don't even need to fine-tune the model now. You can just simply give it a prompt like, is the following product review positive or negative? And just do command review and give the actual sentence. Then model will learn from the context and it will understand and perform the product review analysis by the instruction itself. It is called in-context learning or a few-shot or especially zero-shot learning. For a more complex text, such as explaining why the review is positive, it can use its multi-step reasoning capabilities. It is part of in-context reasoning. So the advantage is that the large language models have unique capability or abilities in context learning or in context reasoning, which only activated in this massive scale of billions of parameters. So the key feature of large language models is known as these three things. And these three things are known to make large language models so powerful. First one is instruction following. So after a process called instruction tuning, large language models can follow instructions for new types of tasks without using explicit examples. You can just give an instruction, then the large language models like ChatGPT will perform as you want. And we also have, large language models also have this feature, reinforced learning from human feedback, RLHF, reinforced learning from human feedback. Actually, you have experienced if you have used ChatGPT. So sometimes ChatGPT asks you, give you two kinds of options of answers and then ask you which one you prefer. That is reinforced learning by human feedback. Human reviewers like yourself or users rank the large language model's responses from best to worst. If you have two options, you choose one that is the best, the rest is the worst. And then by doing so, you guide the large language model to generate responses that are more aligned with your preferences. So that's reinforced learning by your own feedback. Okay, that's possible because the large language models has billions of parameters. It has massive scale. Also, it can learn from the context without any examples. They can learn a new task from just a small set of examples given to them in a prompt at inference time. All right, so we actually face every day AI agent based on large language models. Large language models based AI agents can sense their environment, make decisions, and take actions, right? These agents can go beyond simple response by interacting with external tools and knowledge bases to solve more dynamic and complex problems. Now, let's talk about some classification. So first sort of classification is like foundation model versus instruction model versus chat model. Foundation model is a pre-trained language model with no fine-tuning. As a user, you may not encounter these foundation models. I have used these foundation model for research purpose, but not everyday use. Instruction model is a foundation model that has been fine-tuned to follow specific instructions. And then what we use every day these days is more chat model. This model has been fine-tuned for conversational use, often through instruction and chat fine-tuning. So that's one sort of classification. And the second kind of classification is more technical. So encoder-only models, decoder-only models, and encoder-decoder models. I just wanted to share this idea because I want you to understand the differences between chat models. So encoder-only models are primarily designed for language understanding tasks. They focus on the input, So they take the input sequences and compress it into a meaningful vector. It's called technically embeddings, but anyway, if the model is more like encoder only models, then it understands tasks, or it understands languages better, and it summarizes the text better. It's a super summarizer. I'm not sure about the spelling, but anyway, it's a super summarizer. If a model is a decoder-only models, then these models are designed for language generation tasks. So in this case, it's a super creator. They focus on output, so they take the vector and generate the output sequence step by step. Now there are encoder-decoder models, so it's more improved rather than encoder-only or decoder-only models. These models are unified models designed to handle both language understanding and generation tasks. All right. So let me give you an example of encoder-only models using this example. So suppose input sentence is cats are cute, then let's represent each word as vectors. So let's say cats equals 1 and 0, and R equals 0 and 1, and cute equals 1 and 1. Then encoder model combines these three vectors into one context vector, 2 and 2. Then the whole sentence is compressed into a single meaning vector, 2 and 2. It's really simplified the process, but it's an idea. So it's encoder only models process. Now let's take a look at the process of decoder only models. So decoder takes the output 2 and 2 and generate words step by step. So first output will be cats, and second output will be R, and third output will be cute. Then decoder is predicting each word one at a time. Now, encoder-decoder models will operate in this way. So this is kind of for machine translation. Now let's take an example of translation from Korean to English. This is 고양이는 귀엽다, and the corresponding English is cats are cute. Encoder model will compress the Korean sentence 고양이는 귀엽다 into 2 and 2, and decoder model will use this 2 and 2 to generate the English sentence word by word. Cats are cute. So key process idea of this encoder-decoder models would be understand first, then speak. All right, now let's talk about the limitations of large language models for macroeconomists. So large language models does not have its own memory, so it cannot remember previous prompts. This is an important limitation for many use cases that require some form of state or persistent memory to forecast macroeconomic status for unemployment or inflation or economic growth or GDP levels. Stale information. The models only have access to the information that were trained on, so past information or stale information. They don't know the current time or real-time information, so it has limitations on that side. And the most important thing is hallucination. LLMs are trained to be next token prediction. You can just think about next word prediction. So it is a next word prediction machines. And it can produce plausible sounding, but not necessarily true answers. This is a major challenge for building reliable AI systems. So that's limitations. So we need to check after using or fact check after using AIs. All right. So there are advanced techniques to overcome these limitations. Retrieval augmented generation allows these models to access and integrate external knowledge or real-time knowledges. And prompt engineering involves designing specific inputs to get better outputs. Right? So if you want to read further, I recommend Large Language Models, a survey, and all the pictures in this slide were generated by ChatGPT. All right. Thank you for watching this video.